Welcome to the 1980 Nobel Prize in Physics, which is going to chalk another one up for the particle physicist. This one went jointly to James Cronin and Val Fischer. And what they did was they discovered a violation of a fundamental symmetry principle in the decay of neutral K-mesons, which I know sounds like a lot of weird gobbledygook, but we'll answer a whole bunch of questions about that in a minute. Now, after all this is explained, it's important to understand there are actually some applications and some importance of all this. But really, one of the things this did was it provided evidence of a thing called a strange quark. That's really its name. And it really does help particle physicists in explaining a bunch of the standard model work and a bunch of the other things that have led them to where we are today in the world of particle physics. Now, um, with that, let's dive right in because there's a whole lot of weird words in what they won the prize for: symmetry principles, K-meson, neutral K-meson. What the heck is all that stuff? Well, let's take a dive and learn a little bit of particle physics. Don't worry, not going to be painful, and there is no math, so it's okay. What is a neutral K-meson? First off, what the heck's a meson? Well, a meson is just a type of hadron, which is a particle made up of quarks. Now, that hadron, of course, is just a clump of things made out of different types of quarks. Maybe there's an up and a down. There's even a proton and neutron are a type of hadrons because they're made up of three quarks. So this one's just made up of two. Now, a K-meson is sometimes called kaon. You'll hear it referred to it as both in the physics world. I know we have our own language. We have shortcuts. Everybody has a different shortcut, but K-meson, kaon, same thing. Uh, there's a positive kaon, there's a negative kaon, there's even two types of neutral kaons. Now, a positive kaon is an up quark and an anti-strange quark, which there's that strange quark again, but now we're an anti-strange quark, so it's the antimatter version. A negative kaon is a strange quark and an anti-up quark. Notice the flip-flop there on those two. The neutral kaon comes in two varieties, a short and a long. A short is a superposition of a down and an anti-strange quark, or a strange quark and an anti-down quark, but decays into two different pions. A long has a similar composition, but it decays into three pions and other particles on occasion. And a pion is just the lightest of the known mesons. Now, there's a lot of weird stuff there because you'd think that something that's got a similar composition would kind of always decay the same way. Well, it's not always the case, which is why we're talking about violations of symmetry. Now, what did they win the prize for? Let's really dissect that. So that's what a meson is. Now let's really kind of dig into the work that they did and see why it was Nobel Prize worthy, as they say. So the work. Here's what they found and why there'll be a little bit of this phrasing here that's going to spark some more discussion. For a long time, actually, physicists assume that symmetries characterize pretty much all of nature's. And there's a word there I don't like, assumption. Assumptions can be very, very dangerous things. So you have to be very careful with what you're willing to let yourself assume and what you're not. And I'm not a big fan of assumptions. I'm a big fan of starting conditions, see what happens. So they assumed through these assumptions that we were kind of in this, we lived in this sort of mirror world where left and right are merely reverses of each other, and matter is replaced by antimatter, and the same physical laws kind of apply. And well, I'll agree the same physical laws apply, but sometimes left and right and matter and antimatter don't necessarily flip flop as easily as they should. Left and right symmetry was shown to be violated in 1964 when these guys discovered that that matter and antimatter symmetry is violated with the neutral K-meson decay. So remember when I said sometimes it goes into two pions, sometimes it goes into three and other particles. That's what I'm talking about when you have those different decay chains, but you have a very similar thing. That's not very symmetric. You have something strange going on there. Thus the word strange quark. Uh, Okay, it's not really where strange quark comes from, but I liked it, so we'll let me have my moment. Now, their experiment also proved that symmetry does not apply when you're looking at reactions with regard to time reversal. Bear with me a second. That's a weird phrase. Let's see what that really means in this case, because it may not mean what you think it does. Now, when you look at reactions going backwards in time and forwards in time, you don't get the same things. Now, what does that really mean? It's a physicist way of saying, hey, look, if I start with a neutral K-meson, I may get this chain, I may get that chain. But if I start with like, two hydrogens, and I'm talking about fusion, you can fuse two hydrogens, you get a product at the other side and some energy, and you can reverse that process, at least mathematically. You can reverse that process and get to the original starting point. Here, you can't necessarily do that. So when you look backwards in time, you have these decay particles that came out. You're like, how do I get back to where I was? Well, you can't really do it with the pieces you have. It's like, think of it like taking a car apart and you can't put it back together, even though you know how to do it, because somehow when you took it apart, the parts changed into something else, right? That's what we mean by time reversal. It's not, hey, I can go back in time and, invest in Microsoft when it was just turning public. Hey, I can't go back and become a first round investor in Apple. You can't do that. It's a little different. What we're talking about is time reversal is you can't really look backwards in the reaction chain and get get to the same place you started from. That's all it means. Um, I know it's one of those weird physics language things, but that's what they won the prize for. This one is really just one for the particle physicists. The applications of it are really just in labs. I've never seen or even heard of any kind of practical application for this one, but it really did help us understand a lot of things about particle physics and whether symmetries are the right argument or not. And it turns out in some cases they're really not. And I'm not a big fan of overall huge assumptions unless you truly know what's going on very well. So on original work, I try not to make any assumptions. I always look at it like, okay, we're going in completely blind. I mean, not completely blind, but we're going in with a whole lot of things that we hope happen, but let's not assume anything. Let's just sort of let the data guide us where we want to go because data doesn't lie. I hope everybody's enjoyed this video. We'll see you in the 1981 version. Don't forget to click like and subscribe, and we'll see everybody again soon.